Hi to all of you present here. I am Martin Francis of S7ECB. I welcome all of you to my seminar on the topic quantum computing. I hope by the end of the seminar you would have a very good idea on what quantum computing is and how it's going to change our world. So let's start our seminar. Okay. Now, what exactly is quantum computing? When you hear the name of quanta or something, I think you might have heard of the name quanta many times in your physics class or somewhere else. So basically, quantum computing is it can be described as the computation which exploits the laws of quantum mechanics, and quantum computing is can be described as the amalgamation of physics, mathematics, computer science, and information theory which uses the laws of quantum mechanics to do calculations using particles. And in this seminar, I will be talking about how particles are used and some of the properties of these particles and how quantum computing is done and how it can change our life, how the way we perceive our life, etc. So moving on. Now, in the content session, I'll be giving you a small introduction on what quantum computing is, and then we'll be looking at into the history of quantum computing because we cannot neglect the history of quantum computing. And now after that I'll be talking about what are the importance of quantum computing in this new age, then some of the key concepts of quantum computing, then how can we manipulate the quantum qubits that I'll be talking about in short, then some of the first quantum algorithms, then applications of quantum computing and current works and future scope in the field of quantum computers, and advantages and disadvantages of quantum computers conclusion. Now, moving to the introduction part. So basically, quantum computer is a computer that exploits the quantum mechanics phenomena. And as we all know, our classical computers use something called classical bits. Basically, they are in a state of 0 and 1. But when it comes to quantum computing, we use another particles such which are called qubits, and these qubits can be either an electron, photon, or any other particle which exhibits some of the properties of particles in a quantum world. Now, quantum computing can increase computation so fast that classical computers won't even stand a chance against quantum computing. This is because of some of its properties of qubits such as superposition and quantum entanglement and etc. And I will be talking about that in detail in our next slide. Before that, we'll be looking into the small history of quantum computing. Now, I had given a small history of quantum computing here, and it starts from 1982. Actually, you have to understand that the history of quantum computing only starts from 1982, and history of quantum mechanics cannot be avoided in this. So, I will be explaining a little bit of history of quantum physics or quantum mechanics and how the idea of quantum computer came into being. So, basically, light is something that always fascinated humans for maybe centuries, and there were Greeks who were amazed by the nature of light. Then, in the 16th century, our Newton proposes the idea that a light is made up of particles called corpuscles, famously called as a corpuscular theory. Then Christian Huygens so opposed the idea that he proposed that light was made up of waves, and he is Christian Huygens. When I talk about Christian Huygens, he is one of the one who laid the probability theory that we are using for quantum computing. Without it, our quantum physics would have been incomplete in lot of ways. Now, coming to the 20th century, it started the beginning of quantum physics, and before that, there was a notion that, as we all know, in the 19th century, Maxwell, using his equations, has already proposed that he established that light was basically electromagnetic waves, and he gave us some of his equations, and there was a notion that light was wave, and it was a well established fact until in 1900 Max Planck proposed that energy is quantized in discrete packets called quanta, and it was a revolutionary idea, and even Max Planck didn't like this idea. And it was Albert Einstein, through his photoelectric effect demonstration, that light consists of quanta, This work provided strong evidence for quantization of energy, which was proposed by Max Planck. And it was also Einstein who provided us with the dual nature of light. That is, light is a wave, and both a wave and a particle at the same time. Then in Niels Bohr's model of atom in 1913, he expressed the idea of quantized electron orbits. Then after that, Werner Heisenberg proposed the uncertainty principle, and which was actually very key fact for quantum physics. So on. And we can consider that Max Planck, Albert Einstein, Niels Bohr, and the scientists coming in the generation as the founding fathers of quantum physics. Also, it was Erwin Schrödinger who laid the fundamental equations in quantum mechanics, and he told us how the system works. And we all know, I think most of you might have heard about his cat experiment. And this all laid the works for the quantum physics. Now, coming to 1982, Richard Feynman was one of the greatest scientist, physicist of his time. He was very much obsessed with quantum physics, and he made a key observation that the computers at that time were falling behind calculations, and it cannot do complex calculation including quantum systems. So he proposed an idea that why not make a computer made up of the quantum system itself, that is, use the particles of quantum particles to do calculations. So he was the first one to propose the idea of a quantum computer. Then in 1985, it was David Hughes who proposed the universal quantum computer idea. Then in 1994, one of the first algorithms for using quantum computers were formulated by Shor's algorithm. Before that, Shor also formulated something called a quantum Fourier transform that can be used in the Shor's algorithm. And basically, Shor's algorithm basically breaks the encryption that we are today using. If the quantum computer comes into existence, the basically maybe our cryptographic methods may be broken. After that, Gruber's algorithm does something called a linear search through unsorted database. A marked item is found through the database using the Gruber's algorithm. Then in 2011, D-Wave Systems brought forth the first commercial quantum computer, which actually is a great leap towards quantum supremacy. 2016, IBM opened their way for quantum cloud that can be accessed by public, and it's also a great thing that I think today also we can actually access the cloud and do access their quantum computers and do computations. Now in 2019 is a very big year for quantum computing, and it is Google who claims supremacy in computing. So what is actually quantum supremacy? Quantum supremacy is something in which a quantum computer does a calculation more effectively than a classical computer. And in 2019, Sycamore, the quantum processor or the quantum computer of Google, performed a calculations in 200 seconds, which would take a classical computers eons to complete. And it is a very great leap towards quantum computing. In 2022, it was IBM brought forth the Eagle quantum computer, which uses 127 qubits. You have to look into the fact that in 2019, quantum supremacy was achieved using 55 qubits. 54 qubits. And in 2022, there is maybe a two times increase in number of qubits, and this will go on increasing. And 2022, 127 qubits in Eagle processor of IBM. And within 1 year, within 6 months, IBM introduced another computer which uses 433 qubits, and we can see this number going up in the following coming years. Now you may be thinking, why? What is the need of quantum computing? So there are many reasons for the need of quantum computer. Basically, one of such a reason is the size of transistors reaching the size of atom. So the fundamental, as we all know, in classical computers, fundamental building block of electronic circuit is a transistor. And as per Moore's law, every 2 years, the number of 2 or 1.5 years, the number of transistors keeps on increasing. The problem with this is that Even when the number of transistors are increasing, our processor is reducing in size, and this causes many problems like these transistors becoming more and more small, reaching atomic levels, and in this scenario it can produce a lot of heat and electronic leakage due to quantum tunneling effect. And we cannot neglect the quantum tunneling effect, because quantum tunneling effect is a phenomenon in quantum physics in which electron or a particle can cross a potential at the very thin potential barrier or a potential membrane, even when the electron is even when the electron has less energy than the potential barrier. And we cannot neglect this, because even our transistor works as a switch at some sort of time, and if transistors are becoming small and small, and we cannot neglect one tunneling effect. For example, when transistor is off, there might be some leakage current, and this can affect our computer in very different ways. And now another thing about why quantum computing is that a quantum computer which uses qubits can exist in more than one state. Basically, classical bits exist in a state of or either one or either a zero. But in the case of qubits, basically maybe an electron or a photon, it can exist in two states at the same time. That is, it can exist in the state of 0 and 1 in the same time. And we will be looking into that in detail in next slides. And classical computers are falling behind calculation, like Richard Feynman observed. And there are quantum computer, like in the case of Google Sycamore 2019, helped in solving unsolvable problems in future. Now moving to the next slide, we'll be looking at the key concepts of quantum computing. What are qubits? Then we'll be looking at quantum superposition, then quantum entanglement, and what are quantum gates, and how can we manipulate qubits using quantum gates. Now, qubits. So in the right side, I have given an image of a representation of a qubit into something called a block sphere, and I will be explaining that in detail. Qubit, we can maybe short form, we can call it a quantum bit, and it uses quantum computing and quantum information theory. Unlike classical bits, which can represent either 0 or 1, qubits leverage the principle of quantum mechanics and can exist in the superposition of states. This means the qubit can simultaneously represent both 0 and 1 at the same time, as maybe also as well the combination of these two states in various proportions. Basically, but you have to remember one thing: when a qubit is actually measured, it collapses from its superposition state and into one of the classical states, 0 or 1. Now we'll be looking into the next slide, which talks about superposition. Okay. Now, quantum superposition is a fundamental concept in quantum mechanics that allows quantum system to exist in multiple states, as I have already mentioned, simultaneously. Unlike classical systems, which have definite properties, quantum particles such as electron or photon can exist in a linear combination of states. Mathematically, we can represent it as psi, which is equal to alpha times 0 state plus beta times 1 state. And uh, alpha and beta are two complex numbers which can represent the probability of the two states. In alpha represents the probability, how much probability of getting 0, and beta represents the how much probability of getting 1. Also remember one thing, when we are representing 0 1 in a quantum computing methods, we will be representing 0 as a ket 0 and 1 as a ket 1. So it's basically symbols used to representation of 0 and 1, which varies from quantum varies in a quantum state. While alpha and beta are complex numbers known as probability amplitude, they determine the likelihood of measuring the system in the state of ket 0 and ket 1. Now, I think most of you are familiar with the Schrodinger's cat thought experiment. Often illustrated the concepts of quantum superposition and peculiarity of quantum mechanics. So basically, This experiment can be used to mention how can an electron or maybe a qubit exist in the state of superposition. Okay, basically this experiment covers like this. You take a box, you keep a cat inside that box, you place a poison and a trigger, a radioactive trigger. Okay, then we close the box, and in this time period, in some let us take a 5 minutes time period or some, the cat might be alive or dead when we open the box, and we can only find the result of this when we open the box. And when we open the box, if we find the we may find the cat alive or we may find the cat dead. And if the cat is dead, obviously the radioactive substance might have decayed and it triggered the poison which might kill the cat. Or maybe in the first case the radioactive substance might have not decayed and it didn't kill the cat. Okay, basically before opening the box we didn't have any idea of what was the state of the cat, and we can call it a state of superposition. That is, the cat is dead and alive at the same time until we open the box. Basically, this is how a qubit superposition looks like. Basically, until we measure the qubit, it's in a state of superposition, a state of 0 and 1, both in probability amplitudes. But when we measure this qubit, we get either a 0 or 1 state. Basically, after measurement, we only get classical bits. And one of the important things about quantum superposition is we can actually, using quantum superposition, we can actually represent more data compared to classical qubits. Classical bits. Since they exist in more than one state at a time, we can represent more data using qubits. For example, let us take two bits, a 0 and a 1, and simultaneously we can actually have four states, a 0 1 2 3 state using 2 bits. But we cannot do that in simultaneously in a classical way. Either we can represent one of these states at a time, but using a quantum qubit we can qubit, basically let us consider 2 qubit. Since they are in a position of superposition, we can represent 4 of the states simultaneously, 0 1 2 3 states simultaneously at the same time until we measure. When we measure the values of these qubits, when we measure the value of these qubits, the superposition collapses and goes back into collapses into any one of the 4 states that I have already mentioned. So basically, it's interesting phenomenon, and there are a lot of interesting phenomenon like this. Okay, this is called the Bloch sphere. Bloch sphere is a visual representation used in quantum computing to depict state of a qubit. Basically, I have already told you that psi represents the quantum state and alpha and beta are complex numbers and known as the probability amplitude. But the problem with this that since alpha and beta are complex numbers, we cannot just simply represent them in our three-dimensional plane. So we have to use some other methods, and we use some other methods like we eliminate some global phase and relative phase, something like that, and we reduce the equations scalable for us to learn. So basically Bloch sphere does that, and you can find a small as the arrow goes here, you can find a small equation here. This representation is um, can be used in the Bloch sphere. So cos theta by 2 ket 0 plus e raised to I5 sine theta by 2 ket 1. And so this may look like the spherical coordinate system, and it's the spherical coordinate system, and we can represent these values in the spherical coordinate system and find the state in which the electron is in. Now as the arrow is positioning, I think it is more inclined to the 0 state rather than the 1 state. That is, now consider, if we consider this system in a state of superposition, we can say that this system, when it is measured, it has more probability of measuring a 0 than a 1, because it is more closer to the 0 state than the 1 state. So maybe this has about 20% probability of collapsing into a 1 and by 80% of collapsing into a 0. So points on the sphere surface represent quantum superposition of states. Now moving to the next slide. This is somewhat weird thing about quantum physics. Quantum entanglement is a remarkable and puzzling phenomenon in quantum physics, where two or more particles become interconnected in such a way that their properties are profoundly correlated, even when separated by a vast distance. And this fascinated many physicists, including Albert Einstein, and he didn't like this, and he called this spooky action at a distance. Obviously it's spooky. See, even when we separate two correlated particles, maybe take the example of two electrons. I have two electrons in my hand and I somehow correlate this electron, connect these electrons, and consider that the both of them are in a state of superposition, and uh, I keep one of the electron in my hand, and I leave the other electron maybe billions and billions of light years apart. And when I measure this qubit or the electron in my hand, and I find a spin up state, then obviously I don't have to measure the electron that is for billions and billions of years away. I can, if this is spin up, obviously that would be spin down. So there is some sort of relation between these two. The entanglement forms the basis of quantum gates and quantum computer, enabling complex calculation, and we can do complex calculations using this. Quantum entanglement has practical applications in quantum technologies, including quantum cryptography, which offers ultra secure communication through quantum key distribution, which we will be discussing in a short while. Okay. Now there, okay, I think the spooky action at a distance is very much spooky, because there is a notion that how, I don't know how this communication happens between the electrons. It's so far away, but still they can communicate with each other. And then there is a notion that thought travels faster than the speed of light, and I think something is at work here. Now, moving to the next part, we'll be looking at the quantum gates. Now, like classical computers use classical gates like AND gate, NOT gate. The quantum computers also use gates like quantum gates. Quantum gates are the fundamental building blocks of quantum circuits, responsible for manipulating the quantum states of qubits or the quantum bits. Basically, maybe the state of an electron or the photon is manipulated using the quantum gates to perform various quantum operations. Each quantum gate corresponds to specific unitary operations represented by metrics in quantum mechanics. Basically, we can consider it as a matrix multiplication. Now, I'll be talking in detail about two of the gates, the Pauli X gate and the Hadamard gate. And basically, you can see that Pauli X gate is somewhat similar to the NOT gate that is present in the classical computers. Basically, what this Pauli X gate does is that, consider I am giving an electron as an input to the Pauli X gate from here, and I am getting an output from here. And consider my considering my electron which is in a spin up state, and if I pass this thing through the Pauli X gate, I get a spin down electron. Basically it reverses, or basically it introduces a phase of 180-degree into it, and basically there is not, and this phase is achieved by rotating the Bloch sphere or the qubit in at an angle of 180-degree with respect to the x-axis. So if you have a ball in your hand, you can basically represent it. Simply rotate the qubit with respect to x-axis. You will get, obviously you will get a 180 degrees we phase shift the qubit 180 degree using the Pauli X gate. Now in the case of Pauli Y gate, we do something similar. Pauli Y gate also does the same thing, except for the fact that it it introduces another global phase shift. And in the case of Pauli Y gate, we rotate the qubit with respect to the y-axis, and in the case of Pauli Z gate, we rotate the qubit with respect to the z-axis. And the three of them does the same thing, but the rotation of the qubit is in different axes. Now, if we talk about the Hadamard gate, Hadamard gate does it that the H gate or the Hadamard gate creates superposition in bits, in qubits. So, for example, I'm giving a qubit as an input to the Hadamard gate, and when I receive the output, the Hadamard gate does is that it makes my qubit into a state of superposition, maybe a 50 percentage of getting a 0 or a 50 percentage of 1. If it's an electron, I have a 50 percentage chance of getting a spin up state or 50 percentage chance of getting a spin down state. And we have more of these gates here to manipulate different states of the quantum qubit. Now moving to the next part, we'll be looking at the quantum algorithms, and we'll be looking at the first of the two quantum algorithms, the Shor's algorithm and the Grover's algorithm. Okay. Now moving to that part, quantum algorithms are a class of quantum algorithms specifically designed to execute on quantum computers taking advantage of unique properties of quantum mechanics to perform certain computation more effectively than classical algorithms running on classical computers. Now, when we discuss about the Shor's algorithm was one of the first algorithms developed by Peter Shor, and before that, I think he developed something called the quantum Fourier transform, which is helpful in this algorithm. In 1994, he develops the Shor's algorithm, and it is a great, groundbreaking quantum algorithm designed to effectively factor large numbers into their prime components. Basically, this destroys our RSA encryption that we are using now still today for encryption purposes of our data, which rely on difficulty of factoring large numbers as a core security measure. So basically, what this algorithm does, what RSA does is, they take two large prime numbers, then multiply this, and we get a another large number, and we use this large number to encrypt our data. And by using this Shor's algorithm, we can find these two prime numbers, and if these two prime numbers are found, basically our encryption is broken. Shor's algorithm exploits two key concepts in in quantum computing to solve this. The one is quantum parallelism, and that is the existence of the qubit to exist in more than one state at a time and do computations, and quantum Fourier transform, which was proposed by Peter Shor. And Shor's algorithm has been pointed as a threat if it is brought forth into the world, because if all of our consider the fact that in our country itself, if if some other country develops this quantum computing does develop a quantum computing which can use Shor's algorithm, maybe most of our data might be lost. So I would say it is very much, there are many much security problems which related to cryptography. And since we already know this, then scientists are developing other methods to secure our cryptographic methods, encrypting methods. And I think probably by the time when a very good quantum computer which is basically like a classical computer is developed, we might probably be safe, because we already know the threat, and there are many algorithms coming up. Now, the Gruber's algorithm searches an unsorted database or solves the unstructured search problem faster than the classical algorithms. Basically, it searches through an unsorted database to find a marked item in an unsorted database faster than classical computers. Unlike a classical search algorithm that requires an average n queries, the Grover's algorithm achieved this using root n queries. That is, the number of computations is reduced in a Grover's algorithm. And significance of Gruber's algorithm is that it can be used in many things like optimization, database search, speeding up brute force attacks on encryption. Basically, when it is combined with Shor's algorithm, it can basically destroy all of our encryptions. Now moving to the next part, applications. The application, as I have already mentioned about the Shor's algorithm, but you guys don't have to worry about that. Cryptography, the applications of quantum computer cryptography and security. And now you might have some fear that if a quantum computer is developed, might our data be lost? No, you don't have to worry about that. By the time uh, when a fully fledged quantum computer is developed, another methods like quantum key distribution will be used, or maybe there are scientists who are working on by mathematics of lattice, which uses vectors for encryption, which cannot be broken using a quantum computer. Also, there is something called a quantum key distribution method, QKD method, leverages the principle of quantum entanglement to create unbreakable encryption keys. And if somebody if we find out that we can find out if somebody is stealing our data by just looking at if our entanglement is broken or the superposition is broken or something like that. So you don't have to worry. Cryptography is going to enter into a new era using the quantum computers. Now, in the case of machine learning and AI, quantum computing has the potential of significantly accelerating machine learning and artificial intelligence. Quantum algorithms like quantum support vector machine and quantum neural networks can process and analyze large data sets faster than classical computers. So basically, it can leverage the speed in which we are doing AI calculations. And interestingly, since we are using quantum superposition here, we can have more data compared to previous classical counterparts. Quantum mechanics sorry quantum computing can be used to leverage machine learning by providing more number of data and using methods like quantum neural networks to you do faster computations. Now, in the field of electronics, quantum computing can revolutionize the field of electronics by designing and simulation of advanced electronic components and materials. And we if we can study the behavior and model of materials of quantum levels, we can develop more efficient semiconductors and for electronic devices. Or maybe we can also we maybe in the future we might be using electronic devices which are made up of quantum system itself. So it's also a possibility. Now, coming to the next part, optimization and simulation. Optimization problems which involve finding the best solution for the set of possibility prevalent in various fields for logistic and supply chain management, meant to resource allocation. Quantum algorithms like Grover's algorithm can be used to speed up solving optimization problems that can leverage the optimization issues. Then coming to the next part, finance. And there are actually, if quantum computing is achieved in some way, I would say that we can predict much of the financial models accurately. More accurate predictions and decision making can be done every day. And it can tackle the complex risk of analysis, portfolio optimization, pricing of financial derivatives more efficiently using the financial algorithms. Now, current developments and future scope. And as we already know, the Google 2090 Sycamore processor has already done a quantum supremacy using 54 qubits, and it will increase more and more every year. And talking about the quantum algorithms, there are different algorithms being in development. Shor's algorithm and Groover's algorithm were two of that as such examples. And the right side I have shown an image. It is actually image of the Google computer, and I think the Sycamore processor is embedded in this computer. And then there is something called the variation quantum eigensolver, which basically tells finds the state in which the quantum system is in. Now, industry in this, and there are lot of scope in the industry of quantum computing. Now, mainly Google, IBM, Microsoft, and many other companies are very much involved in the development of a quantum computer, a fully fledged quantum computer, and the application include cryptography, and we can discover new drugs using quantum computers and material science. Now, moving to the advantage part, there are a lot of advantages in the case of a quantum computer. Then there is the fast problem solving, as already mentioned throughout the lecture. It can do faster problem solving. Then it can also do the parallel processing capabilities due to quantum superposition, and it can also optimize abilities due to its if its number of qubits are increased every year. And potential of advanced cryptography like the QKD method or the can be implemented, which can basically protect our data, improving material understanding. We can improve, we can design, or we can optimize our materials, or maybe a very good semiconductors can be developed in the future. The very good use of the semiconductors can be done using quantum computers. Then it's also accelerate machine learning, providing a lot of data to the machine learning models using QNN methods and all. Accurate quantum simulations can be done using quantum computers. Improved climate modeling of climatic conditions can also be predicted, at least at some extent. Advancements in the field of artificial intelligence. Now, coming to the part of limitations of quantum computer, there are some limitations in quantum computer. Basically, there are, for example, error sensitivity. In the case of error sensitivity, errors due to factors such as electromagnetic interference, temperature fluctuation, imperfection in hardware components can be observed. The fragility of the qubits make error correction a fundamental challenge in quantum computing. Decoherence impact. Next is decoherence impact. The loss of quantum information over time. The qubits interact with the environment, and due to this, sometimes the quantum their states may be changed, and it limits the time during which quantum computation can be performed accurately. Now, next is the engineering complexity. There are a lot of engineering complexity in making a quantum computer, basically like specialization of infrastructure and ultra low temperature, precise control mechanisms to control the flow of qubits and all. The next is narrow applicability. As I have already mentioned, I have already told you that if a fully fledged quantum computer is developed, it can change our future. But now the quantum computers can only perform some small calculations, like maybe it can do some calculations, but not in all domains. Quantum algorithms excels in certain domains such as cryptography and optimization, but have limited applicability in other domains, requiring careful consideration when and where to use quantum resources. Now in the next part, quantum interactions, and when two qubits interact with each other, their superposition can be broken, and it can also lead to uh, different errors. Now, error correction overhead. Now, I have already told you, implementing error corrections for quantum systems includes significant overhead in terms of additional qubits and computational resources. Reducing these overheads while maintaining error resilience is a challenging task nowadays, because even when I'm talking about, you can do this much number of calculations using a qubit, but there are a lot of errors, so we need to increase the number of qubits to do this some sort of calculation. Then there are the hardware complexity, such as conducting qubits and trapped ion, and it's difficult to actually make a quantum hardware which can work in right temperature. Then there are also programming uncertain viabilities. When programming a quantum computer, the programming a quantum computer, it is still in its developing stage, and standard programming languages are only being still evolving, and the tools are only being evolving. And you can look at some of the tools, I think, in the IBM cloud or something like that. Now we have actually reached the end of our section. I think most of you guys have enjoyed this session and has a good understanding of quantum computing. And in conclusion, we can say that this technology has the key to our future. We can determine, maybe tomorrow we can actually predict the future. What is going to happen tomorrow using this technology. And I hope we can change our future someday, and it may even it can we can maybe we can use it to avoid disasters, the problems and all. I think you all guys enjoyed this session. I mean, we are going to conclude our session here. Thank you for participating in my seminar, and these are some of my references that I have looked to make this seminar. um, and thank you for participating in this